Hello, what follows here is a fluid mechanical dissection of the operation of Octopus jet propulsion systems using knowledge from introductory fluid mechanics. This isn't sped up, I'm just talking very fast, so you may want to slow down the video. Octopi, when they are in danger or otherwise need to move quickly, are capable of jet propulsion via use of their mantle and siphon. The mantle is essentially a bag of muscles that is able to contract and expand so that seawater can enter and exit on command via the siphon and an opening around it. The siphon is not a fluid mechanical siphon. Here it's just a tube of muscle connected to the body cavity formed by the mantle. When octopi jet, they expand their mantle, drawing in water through a large opening, then quickly collapse their mantle to shoot water rapidly out of their narrow siphon, giving them a lot of thrust from all that momentum leaving their mantle cavity. The model I cobbled up for this real-life system is pictured here. For simplicity's sake, there is only one opening, that of the siphon, through which water both enters and exits. The system is broken down into 5 zones, going from left to right: the siphon exit, the siphon mantle attachment, the mantle, and the rest of the octopus's flesh. The ability of the mantle to expand and contract is represented by a massless, frictionless piston, which when moving will force water into or out of the system. Each zone has a circular cross-section and a length. It is assumed that due to evolutionary pressure, the curving of the exit and attachment zones minimizes viscous losses in said regions. In order to give a goal to this analysis, we will determine what modes of operation maximize A, the ratio of cyclic thrust to power consumed, and B, the cyclic thrust. Since future steps make use of the Bernoulli equation, this system must be operating in steady state, so the piston must move at fixed rates. The piston must return to its original place, so there must be a discontinuity where the piston reverses direction. Further elaboration is captured by this slide. Our goal is to find the best delta and n plus combos that meet our wanted optimizations. When I first attempted this problem, I made use of the control volume conservation and momentum equation, having my control volume cover the outline of the model stretching over the opening. Evaluating the partial time derivative term gives you an acceleration term for the flush of the octopus. Using that, you can get the octopus's thrust, but this requires that you evaluate the sum of the forces on the left, which must include drag. As far as I know, you can't use the drag coefficient method to calculate the drag here because the surrounding pressure gradients in the water are influenced by the water flowing through the opening in addition to the octopus's shape, so this method is a bust for now. The Bernoulli equation with loss provides a better solution. For a streamline going through the center of a straight section of horizontal pipe, the difference in the Bernoulli constant becomes a pressure drop, since by conservation of mass, the velocities on either side of the pipe are the same. This pressure drop can then be converted into a drop in power by simple algebra. Knowing this and the fact that power going out of one zone is power going into the next, we can daisy chain our expressions of loss together, having our streamline be the central axis of the system, to get an equation that relates the power inputted into the cavity by the piston to the energy exchange occurring by flux at the siphon opening. Such allows us to calculate the thrust. All this makes use of the assumption that U and P are uniform along each cross-section, which seems valid since the system easily achieves flows with high Reynolds numbers, indicating lots of turbulence and velocity mixing. The power inputted by the mantle movement is fairly simple. For a piston exerting force on a system with changing volume, the power is equal to force times velocity. From Newton's third law, the force that the piston exerts on the water is equal to the thrust felt by the octopus. This power will always be positive because it will always take energy to move water into and out of the cavity. The power leaving / entering the system by flux is equal to the volume flux times the per volume energy content of the water being moved. This energy content consists of both kinetic and internal energy. However, I will omit the internal energy as A. I will make the assumption that our system is relatively adiabatic, and as a result the only relevant energy exchanges are rooted in the velocity of the water, and B. including the internal energy gives us thrusts on par with the weight of a Saturn V rocket. Some math later, plugging in everything and rearranging gives us the following equation at the top. Dividing the second by UM should give us an expression for the thrust. However, if we do this, the equation now says that no matter the direction of the motion of the piston, the system will always have positive thrust. This weirdness is, I think, caused by the fact that we're using scalars to represent phenomena that are instead best represented by the interplay between vectors, and as a result we've lost key info. A remedy is to make sure the thrust always has the same sign as the velocity, accomplished by the use of the S function here. Having figured out figures for the various parameters describing our system from videos and descriptions of Californian 2-spot octopi, I plugged them into a MATLAB script to determine the duty cycles and impulses that give us our wanted optimizations, as displayed here. Interestingly enough, the optimal duty cycles for each maximization are the same. Also, the max thrust is pretty darn good, but not outside of reason. I don't have enough experience though to comment on the ratio. After having done this, I've learned that while being set on using the wrong equation for analysis results in a lot of wasted time, it really helped me flex my fluid mechanical muscles through me trying to pull out every stop to try and make it work. I also got a hands-on demonstration of why engineers make use of so many approximations. While they result in deviation from reality, they make analyses so much easier and are obvious places where they can be improved. Just going to quickly page through the resources used here. In the description I have linked the MATLAB code I wrote as well as the derivation of my work.